Welcome to the deep dive. Today we're getting into something pretty fundamental in machine learning, especially for analyzing data that changes over time series stuff.
That's right.
You shared some really interesting material. And this comprehensive review paper all about neural differential equations, NDEs.
Yep, NDEs, and they tackle a really common problem. Real-world data, it's often messy, it doesn't arrive on a perfect schedule.
Right. Gaps, irregular timing.
Exactly, and traditional models, well, they can struggle with that out of the box.
Yeah.
So our mission today really is to unpack why NDEs are such a significant innovation here. We wanted to go deep into the core ideas, look at the different types, understand let's say, the academic and theoretical backbone, focusing on what's genuinely new, and also how they work in practice.
And where things are headed. It sounds like a shortcut for us and for you listening to grasp a complex, but honestly really important area of AI, understanding systems in flux.
Precisely. Let's get into it.
Okay, so jumping right in, what's the absolute core difference between these NDEs and, the methods we're maybe more familiar with? Like RNNs or transformers, it feels like more than just a tweak.
Oh, absolutely. It's a genuine paradigm shift. The fundamental difference is how they conceive of time. Traditional models, they process data sequentially, point by point, or maybe in fixed blocks.
Discrete steps.
Exactly. Discrete time steps. They're built for regularly sampled data every second, every hour, whatever. They update their internal state at those specific points in time.
But real life isn't always neat like that. Think medical charts, financial trades.
Right. Sensor data, it just arrives when it arrives. And older models, they need extra machinery to cope. Padding sequences, masking out missing values, special mechanisms to try and brunch the time gaps.
Kind of like workarounds.
Sort of, yeah. NDEs.
Yeah.
They basically throw out the whole notion of discrete steps. Instead, they aim to model the continuous time dynamics of the underlying system that's generating the data.
Okay, hang on. So they're not just connecting the dots we have. They're trying to learn the actual smooth path the system takes between the dots.
That's it, exactly. The central innovation is this. Forget layers transforming states at discrete points. Instead, you have a neural network that defines the instantaneous rate of change, the derivative of some hidden state, continuously through time.
A neural network learns dz/dt.
Precisely, dz/dt, where f is your neural network.
Yeah.
It learns the vector field governing how the state z moves through its possibility space over time.
So the network tells you how the state is changing right now, not just what it might be at the next tick of some predefined clock.
You've got it. And that's why they handle irregular sampling and missing data so elegantly. When you get a new data point, say at time tobes, you don't just feed it in, you use a numerical ODE solver.
Like RunCuta or something.
Yeah, methods like that, often adaptive ones. You use the solver to integrate the learned dynamics that dz/dt function from the time of the last observation, tprev, all the way up to tubs. The solver figures out the continuous trajectory the state must have followed according to the learned rules, no matter how long the gap was or if data points were missing in between. It's inherent in the model. No special handling needed for the irregularity itself.
That feels like a huge advantage for, most real-world data. And the sources also mention something about memory, another big innovation.
Yes, absolutely. This is critical, especially when you're dealing with long time series. Training these models, specifically back-propagating gradients through that continuous solver process, could be incredibly memory-hungry if you did it naively. You'd potentially need to store the state at every tiny step the solver takes.
Right, like unrolling an RNN for thousands of steps.
Exactly. But the landmark 2018 paper by Shen and colleagues, the one that really introduced neural ODEs, also brought in the adjoint sensitivity method.
Okay, adjoint sensitivity. Sounds technical. What's the core idea, the innovative part?
The core idea is massive memory saving. Instead of scoring the entire forward pass history, which for RNNs leads to memory use growing linearly with sequence length, ON, the adjoint method calculates gradients differently. It solves a second related differential equation, the adjoint equation, backward in time.
Backward, so it doesn't need to keep the whole forward path in memory.
Correct. It cleverly reconstructs the state information it needs for the gradients as it goes backward, on the fly. The upshot is that the memory cost for training becomes theoretically constant, O1, regardless of how long the time series is or how many steps the solver took.
O1, memory. for potentially very long sequences.
Yeah.
That's huge.
It's transformative, yeah. Especially for applications like analyzing years of sensor data or very long biological sequences. It makes NDEs practical for problems where LSTMs or GRUs might just run out of memory. It's a major optimization innovation.
Okay, so we have this continuous time view, great for irregular data, and the adjoint method for efficient training. The sources then talk about three main flavors or pillars of NDEs. Can you break those down?
Right. As the field evolved, researchers developed different NDE formulations to capture different types of system behavior. The main ones discussed are neural ordinary differential equations, NODIFORs, neural controlled differential equations, NCDEs, and neural stochastic differential equations, NSDEs.
Okay, starting with the first one, NOD.
NODs. These are the foundation from that Chen et al. Paper. They model the hidden states evolution using a standard deterministic ordinary differential equation. The rate of change, dz dt, depends only on the current time and the current state, modeled by that neural network, ft(zt).
So it's like learning a fixed, deterministic set of rules for how the system evolves based purely on its current state and the time.
Essentially, yes. And theoretically, it's quite elegant. The sources point out it can be viewed as a kind of continuous linnet or an infinite layer version of residual networks, ResNets, which were very influential in deep learning.
Infinite layers, I like that intuition. But deterministic ODEs must have limitations, right? Can they model everything?
Good point. They have limitations. Standard ODEs, when solved, generate diffeomorphic transformations. Think smooth invertible mappings. This means trajectories in the hidden state space can't cross. This can restrict how expressive the model is for really complex dynamics.
Ah, okay. So if the true system involves paths crossing or merging.
NODEs can struggle there. A key innovation that addressed this early on was augmented ODEs, proposed by DuPont and colleagues in 2019.
Augmented? How so?
They simply add extra auxiliary dimensions to the hidden state vector. You essentially give the system more space to operate in. By evolving in this higher dimensional space, the dynamics can effectively go around potential crossing points in the original lower dimensional latent space. It dramatically increases the types of transformations NODs can learn. A clever trick.
Okay, adding dimensions gives it more freedom to model complexity. Makes sense. What's the next pillar then? NCDEs.
Exactly. Neural controlled differential equations, or NCDEs. These came a bit later, with key work by Kidger and others around 2020. The big idea here is to explicitly let the incoming data drive the dynamics. It acts as a control signal.
So unlike NODs where dynamics are kind of internal, here the irregular data arrivals directly steer the state.
Precisely. The formulation changes. Instead of just dzet equals ftez, the state evolution is described using a mathematical object called a Riemann-Stieltjes integral. It looks like n over x. Here, fzt is a continuous path constructed or interpolated from your discrete input data points.
Riemann-Stieltjes. Okay, focus on the concept. What does using that integral do?
Conceptually, it allows the system's state z to change in response to changes in the input path x. When a new piece of data arrives, it causes a change in increment dx in the control path. The model integrates the learn function f with respect to this change in x.
Ah, so updates are driven by data changes, not just the passage of time.
Exactly. This structure is inherently designed for irregular time series. The dynamics are directly controlled by the data stream itself whenever new information arrives. It's a very natural fit.
That seems purpose-built for the problem.
It really is. And people kept innovating. Morrell and others extended this using rough path theory to handle even more jagged, less smooth input signals, neural RDEs.
Yeah.
And more recently, things like log NCDEs by Walker et al. Look at deeper mathematical structures like Lie brackets to better capture complex interactions when the data drives the system. It shows how advanced math is directly improving these models for methy, real-world inputs.
Really fascinating how deep the math goes. Okay, third pillar, NSDEs, stochastic, right?
Right. Neural stochastic differential equations. NSDEs add explicit randomness into the mix. Building on earlier ideas, researchers like Sen and Roginski, like et al., and others formalize this. They incorporate a Wiener process, think continuous time random noise, like Brownian motion, into the dynamics.
So now it's not just the average path, but also the wiggles, the uncertainty around it?
Exactly. The state doesn't just have a deterministic drift f, like in NODEs. It also has a diffusion term, g, multiplied by this random noise dw. So dz.t, ft plus gdw.
Oh.
Both f and g are learned by neural networks.
Okay, drift and diffusion.
Yeah. This innovation lets NSDEs model not just the expected behavior, but also the variance, inherent noise, measurement error, or even potentially sudden jumps or shifts in the system state. things common in finance or biology.
Like modeling stock price volatility, not just the price trend.
Precisely. There's work like neural jump SDEs by G and Benson specifically for modeling those abrupt discontinuities. And a big challenge is making sure this added randomness doesn't make the model unstable or blow up. That's where recent work like stable neural SDEs from OSAL comes in, aiming for robustness guarantees.
So a clear progression. Deterministic internal dynamics, then data-driven dynamics, then explicitly modeling randomness. This all seems grounded in some serious math. Let's talk about those theoretical underpinnings.
Absolutely. These aren't just thrown together, there's a lot of theory. A key lens is dynamical systems theory. NDEs treat learning as finding the underlying equations, the vector field, that governs how a system's hidden state evolves over time in some phase space.
So you're essentially learning the laws of motion for your data's representation.
That's a great analogy. And thinking this way lets researchers apply classical tools from math and physics to analyze the learned models. The sources contrast this NDE approach, learning the rate of change and then solving the equation, which is implicit with other methods like normalizing flows that try to learn the direct mapping from one state to the next explicitly.
Learning the rules versus learning the result directly. And like other networks, do NDEs have that universal approximation property? Can they, in theory, model any dynamic system?
Yes, and that's crucial. Universal approximation theorems provide that guarantee. Given enough capacity, no DEs can approximate smooth invertible functions. NCDEs, especially with rich controls and maybe rough path theory, can approximate a very wide class of continuous paths driven by complex inputs. And NSDEs can approximate broad classes of stochastic processes.
So they have the potential to be very powerful.
They do. And remember those augmented ODEs. That innovation was important precisely because it expanded the class of functions standard NODEs could approximate beyond just those smooth, non-crossing diffeomorphisms.
Right, giving them more modeling power. But potential power isn't enough. You need reliability. What about guarantees that they behave predictably, like existence and uniqueness of solutions?
Excellent point. Existence and uniqueness is fundamental. You want your model, given the same start and inputs, to produce a single predictable trajectory for deterministic NDEs, or at least a well-defined distribution of trajectories for NSDEs. This relies on mathematical conditions on those learned neural networks, F and G.
Conditions like?
The most common one is Lipschitz continuity. Basically means the network's output can't change arbitrarily fast relative to its input. It ensures the function is reasonably smooth and well-behaved.
So it prevents the dynamics from suddenly exploding or becoming chaotic in a way the solver can't handle.
Exactly. It guarantees a unique solution exists, at least locally. For NCDEs, you also need the input control path XT to be reasonably well-behaved, sufficiently regular.
And that ties into stability, I imagine. You don't want small errors blowing up.
It does. Stability is critical. Small noise or errors in the input or state shouldn't cause the model's prediction to diverge wildly. For NODs, Lipschitz constraints help ensure stability. For NSDEs, it's more complex. Stability depends on the interplay between the drift F and the diffusion G. That work on scalable NSDEs by O et al. Is directly addressing how to design F and G to guarantee stability even with the random component.
You want the model to capture randomness but not be overwhelmed by it.
Precisely. And analyzing these complex, often high-dimensional stochastic systems is tough. The sources mentioned using tools from optimal transport theory, particularly the Wasserstein metric.
Optimal transport sounds advanced. What's the gist?
The gist is that it provides a principled mathematical way to measure the distance between probability distributions. So you can use it to quantify how well the distribution of trajectories generated by your NSDE model matches the distribution of trajectories in the real data.
So it's a tool for rigorously comparing the model's overall behavior to reality, especially with noise involved.
Exactly. It helps analyze generalization and robustness in these more complex scenarios. It really highlights the deep mathematical connections being leveraged.
Using optimal transport. Yeah, that shows the theoretical depth here. And one more practical point, since they rely on numerical solvers, solver convergence must be important too.
Crucial. The whole approach hinges on the numerical solver accurately approximating the true solution of the learned differential equation. This can be challenging, especially for stiff systems where things are changing on very different timescales simultaneously. Stiff systems often require specialized, computationally intensive, implicit solvers. Work by Kim, Rakakas, and others focuses on efficient and reliable solvers.
Okay, so deep theory ensures they can work, but practical solvers are key to making them work reliably. Back to training, we covered the adjoint method's O1 memory, which is huge. Any other training innovations?
Well, beyond the adjoint method being the workhorse for gradients, another interesting aspect is the use of integral loss functions. Traditional models often just look at the error at the final time step, or maybe at a few specific points.
Right, comparing the final prediction to the target.
But with NDEs, you're learning a whole continuous trajectory CT. So you can define your loss function as an interval over that entire trajectory. Maybe LA, CD, D, DD, not just LE.
So you can penalize the model if it deviates from a desired path anywhere along the way, not just at the end.
Exactly. It provides much richer supervisory signal. You can guide the entire evolution of a hidden state, not just the final outcome. This actually connects back to classic ideas in optimal control theory, like Pontryagin's principles.
That makes intuitive sense for time series. The path often matters as much as the destination.
It gives you more fine-grained control during training.
Okay, so with all these foundations and training tricks, what's happening at the cutting edge now? And how are NDEs actually performing on real problems?
Well, the field is moving fast, especially in NCDEs and NSDEs. The sources mention recent NCDE work like attentive NCDEs, using attention mechanisms, like in Transformers, to construct more dynamic and relevant control paths from the input data.
Using attention to decide which parts of the input history are important for driving the dynamics now.
Something like that, yeah. And also things like dual dynamics, which explore hybrid models, maybe combining explicit prediction steps with the implicit ODE, solving for better robustness.
Interesting. And for NSDEs?
We see things like latent SDEs, which focus on modeling the stochasticity efficiently in a lower dimensional latent space. And again, that work on stable neural SDEs is crucial for making them reliable enough for complex, real-world applications where stability is paramount. People are constantly finding ways to enhance expressivity, ensure stability, and make them more practical.
It sounds like a lot of integration, bringing in ideas like attention or focusing on guarantees like stability. And empirically, do the benchmarks back up the hype?
The sources reference standard benchmarks, like PhysioNet for medical time series, which is often irregular, and MuJoCo for continuous control tasks. And yes, the results seem consistently strong.
How do they stack up against, say, LSTMs or transformers on these?
The papers consistently report that NDE-based models, NODEs, NDEs, NSDEs, and their variants tend to achieve state-of-the-art or significantly better performance, particularly on tasks involving irregularly sampled data or requiring precise continuous time predictions, lower error rates, better classification accuracy.
Especially where the continuous nature or irregularity is key.
Exactly. The benchmarks seem to validate that the core ideas translate into real performance advantages for the kinds of messy, continuous time data they were designed for. It confirms their suitability and robustness.
Okay, consistent outperformance on challenging data is compelling evidence. But no model is perfect. What are the main hurdles still, and where is research heading next?
Yeah, there are definitely challenges. Computationally, solving differential equations numerically can still be slower and have less predictable runtimes than the fixed matrix multiplies in standard NNs. That stiffness problem we mentioned can really slow down solvers.
The training and inference time can still be bottlenecks sometimes.
They can be, yeah. Making solvers faster and more robust, especially for stiff or high-dimensional systems, is a big focus. Theoretically, there's still work in better understanding how these models behave with very noisy or non-stationary data, and getting stronger theoretical guarantees, especially for the more complex NSDEs.
So improving speed and deepening the theoretical understanding and guarantees.
Right. But the future directions are really exciting. One major area is physics-informed NDEs. The idea is to embed known physical laws, maybe expressed as partial differential equations, PDEs, directly into the structure or loss function of the NDE.
So you give the model a head start by telling it about the known physics of the system, like fluid dynamics or thermodynamics.
Exactly. You combine the data-driven flexibility of NNs with established scientific knowledge. This can lead to models that are more accurate, require less data, are more interpretable, and generalize better, especially in science and engineering domains.
Marrying deep learning with domain science. That sounds powerful. What else?
Another big trend is hybrid architectures. We're seeing NDEs being combined with other successful models. For instance, using graph neural networks together with NDEs to model systems that evolve over both space and time, like traffic networks or climate patterns.
GNNs for the spatial part, NDEs for the temporal evolution?
Precisely. Or integrating attention mechanisms more deeply within NDEs, perhaps to handle very long-range dependencies more effectively than the pure ODE dynamics might alone.
It really feels like NDEs are becoming another fundamental building block, like convolution or attention, that researchers are now composing with other tools.
That's a perfect way to put it. They offer this unique primitive for continuous time dynamics. And now the innovation's happening in how best to use and combine it within the broader deep learning ecosystem. It's a
Yeah.
very active research frontier.
Wow, this has been a really illuminating journey. We started with that core issue. Real-world time series are often messy and irregular, and traditional models struggle.
Yeah.
And we saw how NDEs provide this elegant solution, modeling continuous dynamics by having a neural network learn the rate of change, ZT.
That core idea.
We hit that crucial innovation of the adjoint method, making training feasible with O1 memory huge for long sequences. Then we unpacked the three pillars: NodeDs for deterministic systems, NCDEs driven by the data itself, perfect for irregularity, and NSDEs to handle randomness and uncertainty.
Highlighting innovations like augmented ODEs for expressivity, the integral formulation in NCDEs, and capturing noise with NSDEs.
Right. And we touch on the deep theory dynamical systems, universal approximation, Lipschitz continuity for reliability, stability concerns, even sophisticated tools like optimal transport.
Connecting the math to practical needs.
Plus, training innovations like integral losses and the strong empirical evidence showing NDEs often outperform older methods, especially on their home turf of our regular continuous data.
It really drives home that NDEs aren't just a minor update. They represent a fundamentally different, powerful way to approach time series modeling. They offer this mathematically sound, flexible framework for capturing the continuous nature of many real systems, tackling core challenges head-on.
So, the final thought for you, listening. How does this shift in perspective thinking continuously instead of discretely change how we might model the world? When deep learning's flexibility meets the mathematical rigor of differential equations, what new doors open in science, medicine, finance, engineering? What problems become solvable when we can truly model the flow of time?
It really does open up a whole new landscape for understanding and interacting with dynamic systems. The potential feels enormous.
Thank you so much for guiding us through these sources in this deep dive. It's been incredibly insightful.